I'm going to give an overview of electromagnetic theory. It will necessarily be a little bit shallow, but it should give you an idea of all of the topics that you really need to know in this important subject. We're going to start with Maxwell's equations because these are the foundation of the entire theory, and they contain everything that we need to know. And so just to remind you how these are written, we have the following. We have the divergence of the electric field is equal to charge density divided by epsilon naught. And we'll come back to what we mean by charge density in a little bit. We have the divergence of the magnetic field is equal to 0, which of course means there are no magnetic monopoles. We have that the curl of the electric field is equal to minus the time derivative of the magnetic field. And we have that the curl of the magnetic field is equal to mu naught times current density. Again, we'll come back to the current density, plus epsilon naught mu naught dE by dt. Excuse me. And you'll notice here that we have equations which link the two fields, and we also have equations which show that the sources of the fields are current and charge densities. Everything flows from this. So what we're going to be thinking about in this overview are the sources and also solutions for the fields. If we're thinking about sources, then we naturally have to turn to materials. So we're going to think about the interaction of fields and matter or material, fields and matter. And of course, the point here is that matter is made up of atoms, whether it's a gas or a liquid or a solid. Atoms themselves are made up of positive and negative charges. Of course, you also have neutrons, which are neutral. And those charged particles can move as well as having electrostatic fields, so you get sources of charge and current density. So you have to consider them when you're thinking about electromagnetism. And we defined the following fields, if you recall. So we have the electric displacement, D, which is epsilon naught multiplied by the E field, plus P, the polarization. And we noted that minus the divergence of the polarization gives you a polarization charge density. There is also a surface charge density. I'm not going to put that in at the moment. And we can also write the divergence of the D field is equal to rho E. And I'm putting an E on the row there because this is the external charge density, something which has been added to the material from outside, and that determines the D field. So these equations are always true, and you'll note that we haven't yet specified what the polarization itself is. Sometimes that can actually be quite a complicated problem. You will find in problems you're sometimes given a functional form for the polarization, but then we also, of course, have the case of linear materials. Now, in linear materials, or we should probably say linear, isotropic and homogeneous materials, we write the following. We say that the polarization is equal to epsilon naught chi E times the electric field. You have to be very careful here, because the electric field here is not necessarily, let's say, an external field. So you can imagine that you would take a piece of dielectric material and put it into an electric field. The P that we see here is not, so the E in this equation for P is not that external electric field, it's the total field. And that's important because when you put a material into an external field, you will move the charges around, that will change the field, and that is what we've got to consider for P. And that's quite often why we use the D field to calculate things. We also define the relative permittivity, epsilon R is equal to 1 plus chi E, and we can then define in this material D is equal to epsilon naught epsilon R E. For magnetic fields, magnetic materials, we define B is equal to mu naught H plus M. And here M is the magnetization, whereas just as P is the polarization. In fact, let me just write that up here. And remember that the polarization is a charge density per unit area. It's the density of dipoles in a material. And so if you have a volume density of a dipole, because a dipole is a charge multiplied by a length, the overall dimensions of P are charge per unit area. And here M is the magnetization, which again is the density of magnetic dipoles in the material. H is what's sometimes called the magnetic intensity. and we define that the curl of the magnetization M is equal to magnetization current density. Just as we wrote for D, we can write that the curl of H is equal to J free, and those again are current densities but are not to do with the material. So when we're thinking about doing experiments, H is often the field that we consider because the free current density typically is something that we apply as experimentalists. We will have a coil of wire that gives us that field. Whereas for electric fields, typically we'll be using potentials that we apply, and we'll look at potentials in a moment. We again can define in a linear material, for a magnetic material, the linear field gives us the following. It tells us that M, the magnetization, is equal to chi M times H, and we define the relative magnetization mu r is equal to 1 plus chi M, and so in a linear material we have B is equal to mu naught mu r H. It's important to note that chi E in almost all materials is greater than 0, it's always positive, whereas chi M is both positive and negative, giving you dielectric and paraelectric materials. That's a brief overview of the interaction of fields with matter. The other thing that we have to think about is what happens at interfaces, and that's to do with boundary conditions at an interface. Let me just underline these section headings here, just to make it clear. So at interfaces we have to consider the boundary conditions, and we found by applying various of Maxwell's rules that for both E and H we have components parallel to the interface are conserved, and we should note that for H that is only true when there are no free currents, and for D and B it's components perpendicular to the interface which are conserved, and for D that's only true where there is no external charge at that interface. Those are important boundary conditions which we'll return to. Now let's come back to the question of how we solve for the fields. I've talked about how we think about materials. How do we solve for the fields? One very common approach for solving for the fields is to use potentials. Now in using potentials we note the following. We define B is equal to the curl of A. That's true always, and that comes from the simple fact that the divergence of B is 0 and the divergence of a curl is always 0. So we can always write B is equal to the curl of A. For the electric field E, we write it as minus the gradient of a scalar potential V minus dA by dt. And you can find this actually from Faraday's law. That's the curl of E is equal to minus dB by dt. And the curl of a gradient is always 0, and that all then slots in. From those potentials we can make various solutions. The first set of solutions that we saw were the following. We set the divergence of A is equal to 0. This is known as the Coulomb gauge. It's very often used when we have time-independent fields, and if you do that then we can write the following. For the vector potential, A of r is mu naught over 4 pi, and then there's a volume integral of the current density J. Let's make that an R1, and this is going to be an R2 over R12 dV2. So that's a simpler way of solving for the fields than using the Biot-Savart law. And if we have time-independent fields, then for the electric field, not independent, for the electric potential rather, we can write V of R1 is equal to 1 over 4 pi epsilon naught, and then we also have a volume integral, and we have rho at R2 divided by R12 dV2. And you should notice that these two are really rather similar in form. You've got a 1 over 4 pi and some appropriate constant. You have the source term and you have a 1 over r term. And as we go through the material, you'll notice that this actually gives us an overall link between the fields. Those are very common ways of solving for electrostatic and magnetostatic solutions. The other thing, of course, we can do is we can think about wave equations. We can think about combining the Maxwell equations in order to get a wave equation for a single field. And for the H field, for instance, we find that del squared of H minus sigma mu dH by dt minus epsilon mu d2H by dt squared is equal to 0. And we can do the same for the E field, and it's in fact the identical equation for the E field. If we set sigma is equal to 0, i.e. we consider a vacuum, or actually a dielectric, then we can find that the solution is a plane wave. H is equal to H0 e to the I k dot r minus omega t. K is a wave vector, omega is an angular frequency, and we have that omega over k is equal to c, the speed of light, which is equal to 1 over the square root of epsilon mu, and of course in vacuum that gives us 2.998 by 10 to the 8 meters per second. K gives the direction of the wave, or the direction of propagation, and we can link the two fields using Faraday's law again. You have that K crossed with E0 is equal to omega times B0. And that tells us that K, E and B all form a right-handed pair. So E and B will be oscillating in a plane perpendicular to the K wave vector. And you'll notice that the relative magnitudes of E and B are related by a factor of 1 over C. The prefactor, the vector E0 or B0 or H0, whatever you want, determines not only the amplitude, obviously, but it also determines the polarization of the wave. And in this case, it's the path of the wave vector, the tip of the wave vector over time. So we noted that if E and B are perfectly in phase, i.e. if there's a phase difference of 0, or perfectly out of phase, a phase difference of pi, then we have linear polarization. So if you have the phase difference of 0 or pi, then we have linear polarization. If we have a phase difference of pi over 2 or 3 pi over 2, then we have circular polarization, provided the x and y components are identical. Sorry, when I said phase difference, I mentioned I made a mistake. This is the phase difference between the x and the y components of an individual field, not between the E and the B field. That's me talking rubbish. I apologize for that. So for circular polarization, you need the magnitude of EX, E0x, to equal the we don't actually need magnitudes here, do we? Let me just start all of that again. We want E0x to equal E0y, and all else, all other conditions, it gives us elliptical polarization. So those are plane wave solutions. We can think about the energy and power carried by waves, or by fields rather. The energy density, U, is a half d dot E plus b dot H. That's the energy density. So in order to calculate the total energy, you have to integrate over a volume. And the Poynting vector n is equal to E cross H. And we noted that while it's tempting to think of n as the energy flow across a unit area, the properly defined statement is that the closed surface integral of n is dA is the total outward flow of energy through the surface. And you can also look at Poynting's theorem, which relates the work done by the fields, the energy stored by the fields, or the rate of change with time of the energy, and Poynting's vector. We did then spend a bit of time looking at reflection and refraction at dielectric interfaces. And the key ideas here are to think about boundary conditions. So it's largely optics, but it's optics approached from the background of electromagnetism. So we noted that the refractive index n is equal to the square root of epsilon r. We noted that using boundary conditions and various little simple geometrical arguments, you can find the fact that the angle of incidence is equal to the angle of reflection, and we could derive Snell's law, n sine alpha is equal to n prime sine alpha prime. And notice here that we've got two materials, one with refractive index n, one with refractive index n prime. We have an incoming wave in material n. We have a reflected wave at angle alpha double prime, also in material 1 with the refractive index of n. And then we have the transmitted wave or the refracted wave. And we looked at the Fresnel relations, which related the reflection coefficients, in other words, the magnitude of the reflected wave divided by the magnitude of the incoming wave. And we can also calculate the transmission coefficients, or the transmission, transmission coefficients, of course, are normally the square of r or t, and t is just the ratio of the amplitudes. Fresnel's relations come from the boundary conditions, and they are generally given or easily looked up. The only thing you have to remember is that they are defined in terms of the plane of incidence, which is the plane containing the wave vectors. There's then the question of what happens in conductors. In conductors, we typically have a conductivity, sigma, and we find that the dispersion relation is written as k squared is equal to mu epsilon omega squared into 1 plus I sigma over epsilon omega. So if sigma is very much larger than epsilon omega, which is generally taken as the criterion for a good conductor, then the second term dominates, and we find that k squared is equal to I mu sigma omega. That complex wave vector means that we have propagation into the metal, the conductor, but it's also attenuated, it's weakened. So the magnitude, the amplitude of the wave decreases exponentially as you go into a conductor, and from that we defined a skin depth. We also talked about plasmas, which are materials where you have a freely moving gas of electrons surrounding a set of slowly moving massive positive ions. And there we noted that there was a plasma frequency. This is the frequency at which a plasma responds to a perturbation, which is given by NeQ squared over mass of the electron epsilon naught. And we also showed that epsilon r could be written as 1 minus omega p squared over omega squared, which of course means that k squared is epsilon r omega squared over c squared. And we use this to think about the properties of the plasma below, for electromagnetic radiation above and below the plasma frequency. So if you are below the plasma frequency, then the second term in epsilon r, this term here, will be greater than 1. Epsilon r will become imaginary, and what you have is an exponential decay of the fields into the plasma. So effectively the plasma turns into a reflector. So all of the radiation is reflected. If omega is greater than omega p, then this second term here is less than 1, so this becomes positive, and you have transmission through the plasma. And we briefly mentioned the properties of the ionosphere as an example of that type of behaviour. We're nearly at the end here. We've just got two more ideas. The first one is radiation. Now, radiation is what happens when we allow the sources to change with time. Now, we've up above, we did talk about sources. Let me just go back up to there and think about sources again for a moment. So here we were saying that in Maxwell's equations, we start with rho, the charge density, and J, the current density. We saw actually that polarization leads to a charge density and magnetization leads to a current density. As well as that, when we're thinking about time-varying systems, you do just have to think about the fact that a time-varying polarization gives you a polarization current density. But I won't write that down just here. So now we've got sources which change with time, and in this case we found that we had to do something different for the divergence of A. And so what we have is the Lorentz gauge, and this is where we're wanting to solve for the potentials. So here we say that the divergence of A plus epsilon mu dV by dt is equal to 0. And if you do that, then it's easy to show that you can get the following wave equations for the potentials. Minus del squared of A plus epsilon mu d2A by dt squared is equal to minus mu j, and minus del squared V plus epsilon mu d2V by dt squared is equal to minus V over, sorry, not V, rho, over epsilon. You can then derive solutions, general solutions for the potentials. I'll just give one for A because it's easy to generalize for V as well. So A as a function of R and T is mu naught over 4 pi. You have a volume integral. You have J, the current density, at a position R prime at a time T prime. And it's the time T prime that is important here. Divided by R minus R prime dV prime. And we define T prime, which is the retarded or slowed down time, is T minus R prime over C. In other words, it's a time which takes into account the time interval that light requires to move from the source R prime to the observation point R. So the effect of a change at time T prime is only felt at time T. For V, you write exactly the same equation. It's just you've got 1 over 4 pi epsilon naught, and you've got a rho rather than a J. The other thing that you need to know about radiation is that the B field and the E field should be proportional to 1 over R for radiation. That's because when we take the cross product between B and E to make the Poynting vector, that gives us a 1 over R squared distance dependence. And if you integrate that over the surface of a sphere, it remains constant as you increase the radius of the sphere. If you have any faster fall off, so B or E proportional to 1 over R squared, then as you increase the sphere, the total energy just goes to 0. So that's the criterion that you need. The final thing just to touch on is the idea of special relativity and electric and magnetic fields. And we started by introducing the idea of 4 vectors. So for the position time 4 vector, we write x alpha is x, y, z, and ct. That's what we call a contravariant vector. We write a covariant x lower alpha is x, y, z, and minus ct. And we introduce the rule that if you want to take a dot product or a contraction between 4 vectors, it has to be between a covariant and a contravariant vector. So we write x lower alpha, x upper alpha is x squared plus y squared plus z squared minus c squared t squared. And this is invariant between reference frames. And that leads to a number of rather important points. The Lorentz transforms for this kind of 4 vector can be written as follows. And this is a general form for contravariant 4 vectors. The Lorentz transformations are as follows. You have x1 prime is gamma x1 minus beta gamma x4. x2 prime is x2, x3 prime is x3, and x4 prime is gamma x4 minus beta gamma x1, where we define beta is v over c, gamma is 1 divided by the square root of 1 minus beta squared, and the four vectors we're transforming from, we're transformed to a reference frame S prime, which moves with a velocity v, is equal to lowercase v in the x direction in this case, relative to s. Of course, if the transformation is along z, then the change in the Lorentz transforms, instead of being x1, is x3. Other than that, it's identical. We then introduced a few other four vectors. The current charge density four vector, J alpha, which is simply Jx, Jy, Jz, and c times rho. The potential four vector, which is Ax, Ay, Az, and V over C. There's also the covariant differential, d alpha, which is d by dx, d by dy, d by dz, and 1 over c, d by dt. And from this, you can do various things. So you can, for instance, find that the Lorentz gauge, which can be written as d alpha, A alpha is equal to 0, is invariant. So if you're working with a solution that fits the Lorentz gauge in one reference frame, it works in all other reference frames. We also had the rather lovely realization that you can write essentially all of electromagnetism as the following equation. Box A alpha is minus mu naught J alpha, where box is defined as d alpha, which is just del squared minus 1 over c squared, d2 by dt squared. From all of this, you can then derive transformations for the fields. So the transformations for the potentials here are simply given by this transformation, and that's actually the easiest thing to do. The fields are a little bit more messy. So we find that E parallel primed is E parallel. In other words, if we're transforming to a reference frame moving along the x direction, the x component of the E field doesn't change. E perpendicular primed, so this would be the y and the z components, is equal to gamma times E perpendicular plus gamma into V crossed with B, but the perpendicular component of that. And for the B field, we have that the B parallel primed is just B parallel, and B perpendicular primed is gamma B perpendicular plus gamma over C squared into V crossed with E perpendicular. And we did some little examples here where we were considering a line of charge and a single point charge. That's been a rapid overview of all of the ideas that you need to understand from electromagnetism. So let me just briefly recap by going to the beginning. Everything starts from Maxwell's equations. We introduced the idea of polarization and magnetization. Those encapsulate the response of matter to external fields. In linear materials, the forms are particularly easy, but they are general results. I haven't touched on things like para-electricity or ferromagnetism or paramagnetism, but those are all in the notes. We think about boundary conditions at interfaces. We noted here the solution of the potentials. Those are general. This is a time-independent case. We have wave equations for the fields, which show that we can create plane waves. That's the plane wave form there for H. Of course, these are solutions for light in all its different forms, where you have the direction determined by the wave vector, the fields interact, and you also have polarization. So where does the wave vector oscillate? We've looked at power and energy densities. I've mentioned very briefly the ideas of reflection and refraction and of conductors. I didn't note here, but it is also just worth remembering that as the idea of skin depth, this is just a way of thinking about how quickly the fields decay into a metal. Radiation involves time-varying sources and these general solutions, which typically are quite hard to solve exactly, so there are only a few examples. And then at the end we thought about special relativity, so ways of transforming between reference frames, which actually, when you stop and think about it, shows you that electromagnetism as a whole is a unified theory. There is no such thing as an independent field if you are able to transform between reference frames. I hope that's been a useful summary. There's lots of other videos which are available which go into more detail in these areas.